With these normal curves, there are two things we can do. So what we did in the previous video is with all of these, we were given cutoff values and finding area. So what we were doing with our bell-shaped curve is we were finding area under the curve given some cutoff value and given some direction. But the idea is that we knew where we were landing on the number line, and is that we didn't know the probability or the area. What we're going to do is reverse this. It's going to be the idea with the curve. We know the area, but what we don't know is what is the cutoff value. What is X that's making this line to distribute the percentages or the areas in a certain way? A word that comes through here is the word percentile. So this picture over here is showing a 70th percentile. So we see this line, and then up above that line is 30%, below that line is 70%. So it's the 70th percentile because 70% is the area to the left. And this word percentile, when it's used, it's always describing to the left. So that's always the direction that links with percentile. It's always going to the left. So if you're given an 80th percentile, then I can draw this bell-shaped curve and I divide it such that I have this lower 80%, upper 20%. It's always the lower value. So with this scenario of given area, but then wanting to find these cutoff values, because the percentile is actually the cutoff value that comes from this division, we can still use GeoGebra, and we'll be in the same part of GeoGebra that we were using in the previous slide, and we'll still have to realize, are we doing less than or greater than? In this part, we actually won't be using the bounded between two values button. We'll look at an example where we might be asked that scenario, but within GeoGebra, it freezes because it's a little trickier to move that probability around. So we'll talk about that, but mostly we'll focus on, is it less than or more than? And with the previous scenario, where we were editing the probability statement because we knew the value for X, what's going to happen in this scenario is we're going to edit the right-hand side of the equation because we're going to know this probability that should be coming out, this area, and then what's going to happen is it's going to edit the cutoff value for X within the probability statement in GeoGebra. So let's look at an example with that. So we're going to look at these three scenarios. So we're still working with that Portland rainfall. So we have this normal distribution, mean of 40, standard deviation for 8. And we have these three bell-shaped curves. I'm just going to put 40 at the center of each of them. I'm not going to worry too much about numbering the rest of the line there. So our first question's asking about the lowest 10%. So lowest 10%, lowest values are always happening on the left-hand side. So we want to cut this small percentage, so small area. So we have this lowest 10%, which means if we have the lowest 10%, then equally we have this highest 90%. So it always has to add up to 1. So this would be the 10th percentile because we have 10% of the data to the left. And what we want to do is find what is that cutoff value that's making this 10th percentile. So in GeoGebra, what we're going to end up doing is look for this probability of X being less than or equal to, and then we don't actually know the number that it's less than or equal to. That's our unknown. What we know is that when we plug that in, that area to the left should be 0.1. So let's look at that within GeoGebra. So here's my curve. I'm going to edit. The mean is 40. Standard deviation is 8. And we want to look to the left. So I adjust it so it's shading to the left-hand side. And then I'm going to edit the right-hand side of my equation there. So that's the spot that gives area. And I want that area to be 0.1. And when we do that, it adjusts the probability statement. So we see X less than or equal to 29.7476 is equal to 0.1. So that 29.7476 is our number. That would be the lowest 10% of rainfall is below 29.7476, and we would have units for this. This would be inches of rainfall. So we did here is now we knew an area, and we could find a number along the number line here that cuts off those areas. For B, we have the highest 5% of rainfall. So now what we're doing here is making this small area at the top. So we're on this highest side, and there would be a 0.05 of these highest values, such that if I was shading this area to the right here, that would be covering 5% of our data. If we have this highest 5%, then equivalently we have this 95% lowest values. So that's why this would be considered the 95th percentile. It's because 95% of values are to the left. It's always in terms of to the left. It doesn't matter that they are looking for the highest 5%, that's the same thing as saying the 95th percentile. So we want to do here, and we can look at it either way, either using this area to the left or to the right. Let's go ahead and use this 0.05. So what we're saying here is the probability of x being larger than or equal to, and then for some value, we don't know what that actual cutoff is. For x to be larger than that number, should have a 5% chance. So we need to go to GeoGebra to find that value. So we want this area to the right, and we just need to adjust, so it says 0.05, and that's 53.1588. And that would be inches. So the highest 5% of rainfall is above 53.1588 inches of rainfall. And notice what happens if I had done area to the left. So let's say I switched that. Instead it was area to the left of that 0.95, same exact value comes out. So it doesn't matter if you do right or left. As long as the area is accurate for that direction, you'll get the same number out. Now this last scenario talks about this middle 50% of rainfall. So what's going to happen here is we're going to be stuck between two values. We're going to have this middle, so it needs to be symmetric about the middle, and in the middle is going to be 50%. Which means if there's 50% in the middle, there's going to be 25% in the left tail, 25% in the right tail. Just helpful to have all the numbers there for when we go to GeoGebra. And what we need to find are two values. There's this first x value and this second x value. And we're going to need to find them separately, because if we go to GeoGebra and try to make this middle 50%, notice that when I hit the middle button, that right-hand side locks to where we would usually put 0.5 for that area. It locks because a middle, kind of 50% between two values can happen anywhere. If I move this around enough, I could get close to 50% here, but it wouldn't be symmetric. So making an area between two values doesn't guarantee it to be symmetric about the middle. You can make 50% happen anywhere on this graph. So that's where we need to get a little creative with these areas. So instead, let's say we're finding x1 first. Instead of focusing on the middle 50%, what we can do is use the fact that this 25% must hold true as well. Once we have that middle 50%, those other two values come through. So where x1 creates this middle 50%, simultaneously it has this area to the left of 0.25. So what we can do is in GeoGebra, look at probability of x being less than or equal to make this left-hand side. And then we don't know what, that's going to be our x1 value, but we know that area to the left has to be 0.25. So doing this in GeoGebra is going to give us our first x value. So with our distribution, area to the left, and we need to make that area 0.25. And that's a 34.6041. So that's how we can get that first x value. And then for the second x value, what we need to use is this upper 25%. So we need this area above of 0.25. So to find our second x value, what we're going to do is go to GeoGebra and say the probability of x being larger than or equal to, and then there's our unknown of x2. That area should be 0.25. So going to GeoGebra, making an area to the right of 0.25, and that's a 45.3959. So what we ended up doing is we found these two values that make a middle 50%. And we could double check it if we go back to GeoGebra and say we're between two values. We have that 36.4061. Just let me double check that real quick. 6041. A little mixed up. And then lower bound, we have the 45.3959. And we hit enter. And what did I do? 34. There we go. Good way to double check. There it is. So we have those correct values in there. Sorry, I got a little mixed up switching screen to screen. But if we have those values, we see 50% exactly between them. And maybe that would come out a little off sometimes just because those are rounded values to 4 decimal places. But we get out that exact 50% here. And what we can see is it's nice and symmetric in the middle of that graph. So when we have middle percentages, we have to get a little creative with those tail areas to get to the answer.